Hello, everyone. Thanks for coming to this session. So this talk is on what's new with Apache Pinot and LinkedIn and Uber. About speakers, I'm Yupeng. I'm an Apache Pinot committer, and I lead the Pinot team at Uber. Also in this talk, we have a Sid from LinkedIn, who is a PMC member of Apache Pinot. So what's Apache Pinot? Pinot is a distributed columnar sharded data store, and also is designed for high throughput, low latency analytical queries. You can think of as a real-time OLAP engine. In addition to real-time, Pinot also supports offline and hybrid workloads. And in some of the database terms, you can think of the hybrid as a Lambda architecture. Pinot is a distributed system and it's designed for fault-tolerant high availability and linear scalability. Both at LinkedIn and Uber, we use Pinot for mission-critical use cases, and we have seen good availability from this system. Pinot is an OLAP engine and it supports standard SQL queries, syntax, and semantics. For more information, you can look at the link below, which navigates to the Pinot document official site. Originally, Pinot was developed at LinkedIn and contribute to Apache. From then, it has a really good adoption across the industry. So not only at Uber, you can see there are multiple like big brand names like Stripe, Walmart that have been used Pinot. And Pinot has a really good like scaling numbers, as you can see on this slide from these companies. So just like a quick high-level overview about the Pinot architecture, which is helpful to understand some of the later slides. So Pinot have these three key components and can support both the real-time ingestion. As you can see, the real-time pipelines are from streams like Kafka or Kinesis. And also it support the batch pipeline ingestion from data sets, for example, like Hive or Amazon S3. Look at architecture. One component is the control plane, which is to coordinate the different nodes in this overall system. It's built on top of Helix, which is a cluster management layer over Zookeeper. The data plane is managed by the brokers and the servers. So brokers will take a query and dispatch this to different servers. And server hosts the data and answer this query. So it takes a scatter and a gather approach for querying. So in the later slides, we are going to introduce the new features that in the past few years that we developed both LinkedIn and Uber, and highlight some of the interesting use cases both companies. So in the previous ApacheCon, we talked about Pinot. So these are like to show some latest like developments. So for the first feature we contribute from Uber is on the geospatial. For Uber's business by nature, it's highly real time and also geospatial data relevant. So every day, they are like drivers, riders, eaters, merchants, lots of data are collected and important insights are derived from those. So to make this insights more powerful from the real-time analysis, Uber did a contribution to Apache Pinot. So particularly, we did this in last year. And when we contribute this feature, we try to make the geospatial support to be ISO SQL compliant. There's a standard called like MM on SQL. So this reflects on both not only the data model on the geospatial part, but also the geospatial functions are also compliant to the standard. In addition to this, we also build the geospatial index to accelerate many geospatial queries. This because geospatial queries are usually expensive. Using the geospatial index can greatly improve the query performance. So this index is built on top of a grading library from Uber called H3, which is also an open source library. The idea is that to grade the geospace with hexagons. For example, we can see the diagram below that for each hexagon, it has 6 neighbors, and all the neighbors are equidistant. So such nice property can greatly simplify many geospatial computation and calculation. And there are also like different resolutions of these grids, which are useful to approximate like complex shapes. Like for example, like this is how we use H3 to approximate California on the right. So for the geospatial support, the first thing we added is geospatial data types. Unlike the standard like typing system in SQL, geospatial actually has a complex hierarchy. As you can see, there are like entities like points, curves, polygons, and we add the geospatial types encoded as bytes in Pinot, but we have the full support of the hierarchy. In the engine at the core, we reuse open source library called GTS, which is also a popular library adopted by other open source compute frameworks like Postgres, JS, and also GeoSpark. To learn more about these geotypes, you can take a look at the link, which navigates to Pinot open source documentation. So this is a good example on how you can express this geospatial types using the functions. And for speaking of the geospatial functions, we make this like ISO standard compliant, and all the functions will have the ST underscore prefix. I stands for spatial and T stands for temporal. So here just give us some example to show what kind of functions are. Like you can calculate distance between 2 points, you can calculate area of a polygon. And if you want to read more about this information, you can navigate to the user docs. We also want to highlight the H3-based algorithm. As you can see, the algorithm idea is a bit actually straightforward. So instead of like scanning all the data points over the board, we can actually pick the nearby data points that's within this hexagon, right? And the algorithm takes from finding all the hexagon fully contained in this area, and then we can reduce the data points to be evaluated using this function. So to highlight a real use case of this, recently we published an engineering blog and highlight this carousel, which is like called orders near you. It's an application running in the Uber Eats application. So on the homepage, if you scroll down, you can see this carousel. So originally, this application was launched using Cassandra, which is the persistent store to store all the Uber Eats orders. But because of the design for each incoming user request, it has to make more than 100 calls to Cassandra, which is not very efficient use of the storage system, and results in 60 time increase of capacity if we need to use Cassandra as a storage. And the team built a solution using Pinot. As you can see, this finding nearby orders can be simply described using this SQL query, right? So you take your current point of the Uber Eats user, and you run this function to find all the data points nearby on using both the geo condition and the time condition. So this greatly simplified the application part of building and also improve the query performance by a good extent. Next, I'm going to move to another interesting feature contributed by Uber, which also fundamentally changed the data model part of Pinot. It's called Upsert. So Upsert is actually a pretty common operation in database, right? So before Pinot is built as a immutable store, that means as you ingest events from the real-time stream, data are kept appended. And this feature, we allow people to correct data or update it. And this is pretty important because as I show in this example, that if you want to show a live dashboard to see some aggregates of your Uber Eats and group by the order status, you want to know how many are live now, how many are delivered, and how many are created. Without Upsert, it'll be very challenging to get this information. But with Upsert, we can use this single query to show to do the group by of current status. So there are a lot of use cases can be enabled by this feature. So it's actually a great addition to the Pinot feature capabilities. However, this is a pretty challenging feature to take on. One of the reasons is that on the storage part, we still keep Pinot as a immutable like storage. So this is pretty common for a system that based on like LSM like architecture for good query performance. And with this setup, the key challenge becomes on how do we establish the relationship and connection among the records of the same primary key, right? It's like a lineage problem that you have to update something, you have to find out what to be updated. And then you want to disable that record from your query results. So an ideal approach on this is to establish this global like relationship. Like for example, like given a primary key P1, the record can be on like server 1 or server 2, right? And also like on like server 4. But once you have updates coming in that you want to update this record, these segments by default can be on other servers. So how do you get this global coordination, which is very challenging for distributed systems, especially for the real-time distributed systems. So we take this approach from a different angle and trying to reduce this to a local coordination problem. So the idea is that if you can like partition the data by key, which is an important feature in the Kafka stream, then that means all the records of the same primary key are grouped on the same server, so that this become like a local computation problem, right? So that means all the records of primary key P1 are going to be like on like server 1 and server 2. Then we can derive this lineage using the local computation and greatly solve the important distributed problem. So taking this idea, the architecture shows like this. So once you have an incoming Kafka topic, we want to use some partitioner. In this example, we use a Flink to repartition the data and to shuffle the data within the Kafka stream, and then group the events by the primary key and output to another Kafka topic. And then from this topic, we ingest this to the Pinot servers. So for each of the Pinot server, it will have all the records of same primary key. On the server side, we added a few new components. There's like a local assert key metadata store doing the coordination. And then we added a data structure called like skip doc filter. It's a bitmap based filter so that we know which documents are invalidated because they are updated, right? And then we use this to mask all those documents on the server side. So a couple of words about this progress of this feature. Originally, we attempted this, long time ago, like almost like 3 years ago. And initial approach trying to take the global coordination problem, which turned out to be very complex and results in a lot of scalability challenges. And then we revisited this problem and did a redesign using this local coordination approach. And this time, because of the simplification of the architecture, we made a very good progress on this. So within a couple of months, we added this feature and released this in Pinot 0.6. You can find out some of the links here that on the release notes and on the design documentation. We are also made a follow-up development on this, which called like partial upsearch, so that for changes, you do not have to have the full payload of the entire row, but can only like describe what value to be changed on select columns, and you can ignore the others. It's called like partial upsearch. So we just made a contribution into the Pinot main trunk, and this will be released in 0.8. So give you a quick example to see what this is like running upsearch. So we want to select from the its orders, and are interested in one particular like ID. So before the upsearch, you can see the full history of this order from created to assign some drivers, and then this become pickup. With upsearch, we only show the latest status of this. All right, so now I will pass this to Sid to talk about the awesome feature developed by LinkedIn.
Okay, thanks, Yuping. Yeah, hi guys, I'm Sid, and I'll be talking about a couple of features that were contributed to Pinot by LinkedIn and how they are being used at LinkedIn in production. So the first is the text search support in Pinot. So to set some context about text search, let's just go over how an exact match search operation happens in Pinot. And let's say you have a column called as first name in your table, right? And there is no index in the table, and you have a simple query where you want to count the number of rows in the table where first name is John, right? So the Pinot segment has a data structure called as dictionary, and dictionary basically is essentially the length of the cardinality of the column. So there are as many values in the dictionary as the number of unique values in the first name column. So first we basically look up the dictionary to find the dictionary ID of John, and the dictionary is sorted structure. So we do a binary search. In this case, the dictionary ID is 2. And then we scan another data structure in the Pinot segment called as forward index. And we basically scan the forward index row by row, and as and where the dictionary ID 2 is matching, those rows are getting selected. So since this is an exact match search operation, and since there is no index, we basically end up scanning the entire table. Okay, so now let's see how the exact match search happens if there is an inverted index, right? So it's the same setup. You have the first name column in your table, right? And this time you have an inverted index on this column. So let's say the user is interested in the same query, wants to find out the number of rows where the first name is John, right? The steps are same. You first look up the dictionary using binary search to find John's dictionary ID, right? And then you basically, instead of scanning the forward index, we do a lookup in the inverted index on where the key is the dictionary ID. So we look up the dictionary ID 2, and we get a bitmap of doc IDs, right? And so that's it. That's the answer, right? We don't end up scanning the forward index row by row, right? And the inverted index helps us fulfill this query multiple orders of magnitude faster, right? So this is how exact match search operation happens in Pinot without index and with inverted index. Now, let's say the user is not interested in doing exact match. User is interested in doing a bit of arbitrary text search, right? So in this case, the user is interested in finding out, counting all the rows from the table where the first name starts with John. So it's a prefix query, right? And to support these kind of operations, Pinot has exposed a function called as regexp like, and the processing is more or less the same. So in this case, what happens is that you first, since there is no index, right? So you have to do a scan. So we first scan the dictionary, and for each unique raw value that we have in the dictionary, right? We get the raw value, right, from the dictionary. Then we do a Java regex based pattern match of the raw value with the regex that is specified in the query function, right? And we find out all the matching dictionary ID set. Then we scan the forward index data structure and count the number of records with the dictionary ID part of the matching set, right? Because each cell value in the forward index is a dictionary ID, so we just need to check, okay, is this dictionary belonging to the matching set that we computed in the set to? Is this dictionary ID part of the matching set? So that's how we do an arbitrary text search when there is no index. So the key takeaway here is that indexes are not used to evaluate regex filters, and we use scan. Okay, so now how do we actually make this operation efficient, right? How do we run the text search operations efficiently? So mostly when the text data is arbitrary, let's say you have like textual blobs, right, or globs, where each column value is like a heterogeneous text, we need more than exact matches. Users are mostly interested in doing regex queries or phrase queries. Phrases are basically multiple terms combined in the same order, or fuzzy edit distance like queries on your textual data. In addition, they also need the ability to easily compose a single complex Boolean search expression consisting of one or more kind of text searches like regexes, phrases, etc., etc. So the existing function, which I showed in the previous slide, regexp like, has a couple of issues. First is the poor latency because it uses scan without, and there is no index, right? And so most queries time out during execution when filtering large amounts of data. The other drawback is that regexp-like is based on the Java regex syntax. So it is very non-trivial to compose a single complex Boolean search expression, let's say where you have like 5, 10, or even maybe hundreds of clauses, which we have seen in production. So then writing that in a regex query easily gets non-trivial and less usable for the user. So to solve these issues and make the text search super efficient, we added support for text indexes in the 0.3.0 release of Pinot. So let's quickly go over the performance of a text search query without and with the index. So here we have taken the sample data set of size 500 million rows and filter selectivity of 150 million. So by filter selectivity, I imply that how many rows are going to pass the filter. So that's 150 million. And as you can see, the text search with scan, right, takes about 8 minutes. And then with index, it takes about 2 seconds. So it is definitely like multiples orders of magnitude faster than the scan query. So the text search support in Pinot was contributed by LinkedIn. It is supported on string columns for both offline and real-time tables. So you can use your text search on batch uploaded data, or you can do a real-time text search. It is heavily used in production at LinkedIn for keyword-based search on LinkedIn Talent Insights platform. So LinkedIn Talent Insights platform uses Pinot to compute various talent-related metrics and allows the users of the platform to understand various macro trends across the different talent pools and understand the talent landscape and basically define a hiring strategy. Now, the users of this platform, they wanted some flexibility to be able to uh, construct broader searches and generate wider variety of the talent pool metrics, right? And be able to define a better hiring strategy. Now, the text search feature that is added in Pinot allows the uh, LinkedIn Talent Insights users to search for pretty much any text on a LinkedIn member profile. The text could be in your skill sets, it could be in your description, or it could be in your title, could be anywhere. And with this free form text search, they are able to analyze the talent pools for different emerging skill sets, tools, technologies, and they are also able to put together very complex Boolean searches very easily and analyze and isolate various kind of talent pools. And the users of this platform have described this ability to be able to do free text search on the profile along with the standardized search, which has already been there, right, as a game changer for the talent analytics. So it has really improved the user experience and their hiring strategy. Okay, so now how do you really use text search in Pinot? So it's a part of our standard SQL query syntax. So let's say we create a table with two columns. One column basically has a Pinot broker query log, where each column value is a line from the query log, and then another column where each column value is the candidate's profile or resume, and we can store both the columns as string type and enable text index. Now, the first query could be to count the number of queries in the log file that have, let's say, between filter on time column, and they use group by. So let's say you want to do this kind of text search analysis. Then it's simple, right? You just do select count star, and then we have exposed this function called as text match added to our SQL grammar. Specify the first argument as the column on which you have text index, and then your search expression. So as you can see, it is fairly straightforward to compose a Boolean search expression. Then let's say you are interested in finding the number of candidates that have skills, machine learning, GPU processing, and maybe one-off distributed systems or TensorFlow. So again, it becomes like a Boolean search expression and standard syntax of using and, or, etc. You can compose any length or size of a search expression. Next, I'm going to talk about how you can use theta sketches for a different way of doing approximate distinct counting in Pinot. So let's say what is really distinct count here, right? So common use case, it's a very common use case in the OLAP queries to count the number of unique values in a column, right? Let's say you have a column, let's say, I don't know, member ID or something, or right, and you want to find out the number of unique values, and you may have a group by on one or more other dimension columns. Now, Pinot SQL provides multiple functions for unique counting. The first is your accurate count, where we have provided this distinct count aggregation function, which gives you a very accurate count of the number of unique values in the column. Now, as the cardinality of the column is increased, or if the volume of the data is high, then this operation becomes very memory intensive, as well as the latency increases for the query. So then we have another alternatives for approximate counting. So hyperlog is a commonly used data structure in databases, and it trades off memory footprint and performance for approximation. So the query uses lower memory footprint, right, and a better performance, but the result is approximate, so it is not accurate. Then we also added a third variant of approximate count, which is called as distinct count theta sketch. And this uses Apache data sketch library. The key difference between this and the distinct count HLL is that this also supports your set-based operations like union, intersection, and things like that. So this feature was contributed to Pinot by LinkedIn. It is used in production for a audience reach estimation use case, like where, let's say, you given a targeting criteria, right? The businesses want to estimate the reach of an advertising campaign. They want to find out the number of members that this advertising campaign will reach, right? And these insights are surfaced to these users via LinkedIn Campaign Manager product, uh, where the users can define their targeting criteria, and the targeting criteria can be defined on the basis of member attributes. For example, you can define a targeting criteria, let's say for members who live in either US or Canada, they work for LinkedIn and they know Java or C++. And you can create an advertising campaign for this and then use this audience reach estimation use case to find out the estimated reach for your campaign. Now, what is a targeting criteria? It's essentially a logical combination of various conditions, and each condition represents a set of members. Okay, the set of members in USA, a set of members in Canada, a set of members that have worked for LinkedIn, set of members that know Java, right? So then audience reach estimation problem essentially boils down to finding the unique count of members in the intersection of these multiple sets, right? So then the initial working solution that we came up with basically was a distinct count based aggregation for unique member counting, right? And our source production table was pre-aggregated to reduce the number of rows. So as you can see in the schema, we had various dimensions like your country, skills, which is a multi-value column, and many other attributes, then industry, and then the count, which is the number of members with that particular dimension combination. The challenges here were that since many of the columns, dimension columns, were multi-valued, right, and high cardinality, along with the constant addition of new attributes plus with the organic growth in membership, we saw linear increase growth in the table size. Secondly, every day the entire Pinot table data is refreshed, essentially overwritten with newly generated member data. And this growing data volume along with daily refreshes just increase the data push latency and put the data freshness SLAs of customers into an acceptable range. And so that those were the key challenges around with our initial solution of simple distinct count based query. And as you can see, the SQL query is fairly straightforward, right? Here you can use the select some count from table where country in US, Canada, and your skills in Java, C++, and company equal to LinkedIn. So basically just computing, just doing a sum count on the pre-aggregated data, right? So now in order to tackle these challenges, we had to rethink the data schema, first of all, to reduce the data set size and also be able to improve the data freshness SLAs for the customer. So we started exploring approximate distinct count solutions. The first one we explored was the distinct count HLL. Now hyperlog as I mentioned, scales well, lower memory footprint, better performance. But the main problem over there as far as functionality is concerned is that it does not support set intersection operations. So that's why, and as I mentioned, right, we needed to be able to intersect the member IDs belonging to different sets for an advertising criterion. And so that's why we started exploring this theta sketch based solution. So similar to hyperlog, theta sketch is again a very probabilistic data structure uh, doing the optimize for time space trade-off, right? And it is a solution for approximate distinct count, just like hyperlog, but supports the intersection. So what we did is that we pre-computed a serialized sketch for each member dimension value, right? Let's say it is USA, country equal to USA or skill equal to Java, right? And then we stored that as a bytes blob in the Pinot table. And our new schema has 3 columns, which I will show in the coming slide. And this led to a very, very drastic reduction in the data size, improving the data push latency and the data freshness SLAs. Also, one other benefit of this solution is that because even if, let's say, you're adding members, right, or you're adding member dimensions, the schema of the table doesn't have to change. So our new schema is essentially you have first column as the dimension name, let's say country, company, skill, right? The second column is the corresponding dimension value. And then the last column is the serialized sketch, which is essentially a bytes data structure comprising of all the representing a set of member IDs belonging to that particular dimension, right? So now how does the execution happen? Servers essentially compute the union of all qualifying sketches for the where clause. So the where clause will look like standard. You want to do a union, so you want to do, okay, where the dimension name is country, right, and dimension value is USA. So it will select the sketch for this condition, and you combine with or, okay, you want to look at, okay, dimension name is company, right, and dimension value is LinkedIn. So then the union, all the union of these sketches will be selected by the server. Then at the end, we want to do an intersection, right, or any other set operation for that matter. So we want to provide that set operation as expression to the aggregation function. And then the Pinot broker computes the set operation on the resulting sketch. And that's how it estimates the set intersection cardinality. The brief insight into the performance that we were able to achieve. So the P95 query latency was around 800 milliseconds for 20 QPS. So now, as you can see, how has the query changed? We have introduced the distinct count theta sketch based aggregation function in the query, right? And you have provided a set operation as an argument to the function. And as you can see here, we are using AND. So that means the broker will compute an intersection over the unionized sketches that are sent by the server. And then the same where clause for the union that is mentioned above for the server execution. So that's what the new query looks like on the new schema and with theta sketch based execution. So that is pretty much for the text search and the theta sketches. Over the last couple of years, LinkedIn, Uber, and many other open source contributors in the community have contributed several other features to Pinot. Some of them being like we have moved on to being standard SQL compliant syntax and semantics as far as the query language is concerned. We also added support for um, one particular variant of join called as lookup join. Then we added support for JSON indexes, having clauses, a lot of work on the type of functions like transforms during ingestion and post aggregation functions, killer functions. So these are the kind of features that we have added and many more over the last couple of years. And here is a link that we have given to our release notes for the open source Apache release. Then here we have given references to a couple of blog posts that we have written. The first is the blog post that recently came out by LinkedIn on how the text search is powering the LinkedIn Talent Insights use case in production. Then the second one is basically going into the lot of internal details and of design details and implementation for text search. And we have also a blog post on the theta sketches and how it is used in production for the audience reach estimation use case. We have a couple of nice blog posts by Uber on the geospatial indexes and how it is solving a key production problem. Yuping is giving a talk next week at the Kafka Summit on how is Upserve solving the real-time analytics problem. And then lastly, we have a link to the Pinot user docs. That is pretty much. Thanks a lot.